You are recording, so that should come up here on this other. Does it? You are recording. Good. It should work. And yeah, here we go. It has. Yes, you are right. It has a little bit of a delay, but hope it's not too bad. And I will share my screen with you. And oh no, I don't want you to see my emails. That's not the right thing. Where am I? Am I here? Yes, I'm here. Okay, and can you see the screen? Does that work as well? Yep. Wonderful. So what else can go wrong then? Not a lot, I guess. And everybody is muted. Life is good. I used that as a catchphrase a couple of years ago in one of the in this module, and ever since it follows me. And students, even when they email me, put that sort of in their email. Life is good. Well, at least it made some impact. And I need to turn off this bling here. It drives me insane. I don't know whether they were lying. They just thought it's a sort of a strange catchphrase. Uh, I hope they were not lying, because, I mean, if you look at it, life isn't that bad, actually. It could be much worse. And when people say to me, I had a chat this morning with a fellow dog walker at around 6-ish, yes. And he said to me, he thinks 2020 was such an absolutely shite year. And I think a lot of people would agree, but I see it in a slightly different way. I mean, yes, it was different to what we usually experience, but then this year really forced me to do things differently, to see things in a different light. And at the end, 2020 actually forced me to grow, whether I wanted it or not, explore new things and discover new things, learn new stuff. So I thought you can give it a positive spin as well. So, and I think we probably get cracking. It's not too challenging what I'm going to do with you today, but it's going to be really, really important. But please, yes, I agree, Bernardo. But let's not go into these things at the moment. I just want to spread a little bit of positivity, and with that, I don't mean COVID positivity. So I want to do with you buffer calculations, but please don't forget to record your attendance in Moodle. And why do I want to do this calculation with you and show you how it's done properly? For two reasons. One is it will definitely hit you in some assessments. You will need to be able to show me that you can calculate the components of a buffer. And you will also need these skills in a practical, and we are currently thinking about how we run this practical next term. But you will need these skills, but especially you will need these skills in the next year when you do what we call a mini project. you have to make a buffer yourself. And in your final year, when you do a lab-based research project, then inevitably you have to make buffers yourself. They will be prepared for you. And in the last session, we actually discussed what a buffer is. And I told you a buffer has the function of keeping the pH of a solution more or less keeping the pH of solution constant. So even if we add some acid or some base to that solution, the pH in the presence of a buffer will not change dramatically. And I demonstrated that to you by looking at two solutions. One was with a buffer, one was without a buffer, and we added protons to both solutions. And in the case of no buffer present, the pH changed dramatically, whereas in the presence of a buffer, the pH changed slightly, but not that dramatically. So whenever we do any kind of experiments with, for example, cells or even just basic solutions, we would usually use a buffer to keep the pH more or less constant, unless we want to investigate what a pH change actually does. But usually, when we are working with cells or with organisms, with microorganisms, bacteria, or anything like that, we do not want the pH to change dramatically. And we are also we need buffers for our everyday life, because we know, for example, that in the blood, we need to have a very, very specific pH, which is around 7.2 or something like that. If the pH in the blood changes only marginally, say by 1 pH unit, so it drops to, instead of 7.2, it drops to 6.2, death is absolutely certain. No person can withstand a change of 1 pH unit in the blood. So the blood actually needs to be really tightly controlled and buffered. So absolutely, it would be fatal. And we can all think of situations where, for example, the blood would be inundated with protons. So if we release protons into the blood, the pH would change dramatically. Can you think of something that would change actually the proton concentration in the blood? Can anyone think of that? Running, yes, that's a very good idea. Why running? Because you breathe out carbon dioxide, yes, to a certain extent, but yeah, exactly, it is. You're right. You build up lactic acid, and lactic acid is an acid, and therefore it will release protons. And the lactic acid is a product of a biochemical pathway, which we will discuss in a lot of detail next term. You convert glucose to lactic acid. Glucose is not an acid or a base. Produce an acid from that, and that will make the pH more acidic. Another thing is also if you suffer from diabetes, you produce lots of organic acids, and therefore, if the diabetes is not controlled properly, you will suffer from acidification of the blood. So therefore, buffers are absolutely important, and we will also discuss, we make a link tomorrow in tomorrow's session to what we have discussed in the BI 300 module, where we then look at amino acids and proteins, how they behave in different pH situations. But for today, I want to do with you calculation, and I show you how we can actually break down what looks like a rather complicated calculation. In the first place, I have shared with you, I think, a document that I've done over the weekend that gives you the different steps how to make up a buffer. But I thought it might be useful to the different steps when we need to make up a buffer solution. So here is the question, and I've chosen a really, really simple question because I want to do that. I thought I put it. Did I put it up on the Teams? Or don't worry, I will send it out again, probably via email or via a BI 308 Moodle announcement. So don't worry about it. So let's go through that. So at least then you have a good understanding of how we are looking at these things. Good, yeah. I don't want to overload you with emails. I know that you get a lot of emails, but if you don't mind me sending out emails, then I'm quite happy to do that. And I might also do a cheat sheet to tell you what you need to revise for the okay, good. For the BI 308 test in week 12. Do you want such a cheat sheet, a checklist? Okay, good. I will try if I can cobble something together. Yeah. Okay, so here's the question. We have a pKa of a weak acid, and let's just simply highlight things a little bit. So we've got a pKa, and the pKa of this weak acid is 7.5. I will talk about the assessment at another time. Don't worry, it will be very different to what you are used to, and it's not a multiple guess test. So pKa of a weak acid is 7.5. The pH of the buffer that we want to make should be 6.5. The total capacity of the buffer should be 220 millimole per liter. We have an acid with a molecular mass of 123 grams per mole and a base with a molecular mass of 143 grams per mole. And we want to make 100 milliliter of this buffer. So the question is, how much of the acid and the base do we have to weigh in? So what is this question actually asking us? The question is asking us to make up a buffer, and we want 100 milliliter of this buffer. So that should be 100 milliliter at the end. We want that. And the pH of the buffer should be 6.5. That is what we want. The buffer should also have a capacity. Capacity should be 220 millimole per liter. Okay, so this means, since we are dealing with a buffer, we are working with an acid, and let me write this like that. That is our acid. And we know a buffer is a combination of a weak acid and the conjugate base. So we've got an acid and the conjugate base, and we know what a conjugate base is. It is the acid minus the proton. So we would have A minus. So that would be the base. And it has to be the conjugate base. So we have to have a conjugate acid base pair. And we discussed what that actually means. So we want together, we mix these two substances. We said the base has a molecular mass of 143 gram per mole, and the acid has a molecular mass of 123 gram per mole. And now the big question is, how much of the acid do we need and how much of the base do we need to put into our solution so that we get this buffer with these specifications? That is what we want to have at the end. So how can we actually do that? We also know that the pKa of the acid is 7.5. So let's say, right, we are dealing with a buffer, and therefore it's always a good idea to write down the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. And you will always use that when you are working with buffers. And the Henderson-Hasselbalch equation tells us the pH of a solution equals pKa of the acid. And I just simply, I do it with negative. Minus the logarithm to the base of 10 of the acid concentration divided by the base concentration. Okay, that is the Henderson-Hasselbalch equation, and you really need to know that thing. So before we get started, which way you write it is absolutely entirely up to you. So you can write it as a positive sign here with the logarithm, but then you have to change the acid and base in the log. So it's exactly the same as pH equals pKa plus log base over the acid concentration. Both things tell you exactly the same thing, and it doesn't matter which one of them you use, as long as you can remember it. So, the first step that we need to do, what am I writing here? Let's say step one. Step one. Before we get excited and do any calculations, we do a quick non-calculation issue. Because what we are going to say is we have the pH should be 6.5. We've got the pKa, that should be 7.5. We know that the pH in this case is smaller than pKa, because 6.5 is smaller than 7.5. Therefore, we know that we need more acid. If, which we don't have here, if the pH was larger than the pKa, we would need more base. Okay, does that make sense? And if the pH is the same as the pKa, we need equal amounts of acid and base. Why? Well, the answer to that is just simply in the Henderson-Hasselbalch equation. Let's have a look. If we say pH equals pKa minus log, and we now use the same concentrations of acid and base, does it still work? Can you see it? Really? I can't see anything. Okay, good. Tell you what, I quickly get out of it and then wait a moment. Let's see. Let me go back. Aha. Screen broadcast. Good. Okay, good. Share screen. Okay. Is it working now? Are we back? Yay. Hey, cool. Okay. If we have the same amount of acid and base, what will happen? Let's say we have the concentration of 10 millimolar for the acid and the same concentration for the base, 10 millimolar and 10 millimolar. What do we get here in this bracket? What is 10 divided by 10? Well, that is, of course, 1. So we've got log 1. So pH equals pKa minus log 1. What is log 1? Zero. Does it move? Does it work? It's probably the dogs downloading YouTube videos. Mind you, sometimes I'm not necessarily writing anything, I'm just talking. Okay, let me see. Can you see anything? I've just written a smiley face. Okay, I tell you what, I will leave and restart the whole thing, okay? Let's see if we can get this sorted. Don't panic.